welcome everybody to today's webinar. My name is Dan Combest. I'm the manager of ENGYS here in the US. And today I'll be talking about surface optimization with continuous adjoint. Some of today's goals, I'd like to kind of continue to build on demonstrating adjoint innovations at ENGYS and show a few customer success stories with HELYX Adjoint, and then demonstrate how to set up a simple surface shape optimization case. So we'll save the questions to the very end, and we can continue to answer questions via email. All you need to do is hit reply on the meeting invite, and it'll go directly to me, and then I can respond to you. Just a little bit about ENGYS. We are global providers of CFD software services and products. We were founded in the United Kingdom in 2009, and we're just celebrating 10 years of business. Since we started, we've always been focused on enabling open source software in industry, specifically working on foam and open foam, and we've been developers with that code base since 1999. So if you're familiar with open foam, you know that it started in around 2006. Before that, it was a closed source code called foam. So we've had developers at ENGYS working with that code base since before it was even open source. We have 7 offices worldwide: the UK, Germany, Italy, here in the US, Australia, South Africa, and Brazil. And we have an established distributor network around the world in Japan, South Korea, here in the US, France, and also in Spain. Just a little bit of information about our products. We have 4 main product groups, the first being HELYX, which is a general purpose open source CFD software suite. And this includes a mesher, it includes some post-processing. You can set up problems and solve them. Elements is an advanced open source CFD software for automotive design. This I would categorize as basically a superset of HELYX. In addition to the general purpose CFD interface, you also have automotive specific tools like templates or workflows that are related to external aerodynamics. And it speeds up the process of setting up vehicle aerodynamics, specifically cases, tremendously. Next, we have HELYX add-ons. Today, I'll be talking about the adjoint optimization add-on. We have other add-ons for block-coupled solvers, marine hydrodynamics, which will be our first webinar in May, and then also another add-on focused on advanced multi-phase flow solvers. Finally, we have HELYX OS, and this is an open source GUI for standard open foam. This is available for free. You can go to our website and look at our products to find the link where HELYX OS is. It's hosted on GitHub, so you can download the source code. You can download an executable to run on Linux. Just a little bit of information about some upcoming webinars. We have one webinar, like I mentioned, in May, and this is about open source CFD solutions for the marine industry. So one of my colleagues, Paulo Jeremia, will actually be the speaker at this event. So today, I'd like to talk about continuous adjoint, talk about shape optimization, give a few examples of success stories, and then do a demonstration of setting up a simple case within the GUI, and then leave you with a few take-home messages. So if you haven't been to one of these webinars before, I've done several adjoint webinars previously. I did one called Improving Engineering Design with Topology Optimization, and then I did another one recently on Enhanced Topology Optimization with Multi-Objective Continuous Adjoint. Both of these, you can view the webinar, you can read a little bit of notes that I wrote out. You can see blog.engys.com for more information. In terms of continuous adjoint, a lot of times when we talk to people, we focus a lot on where's the opportunity to actually use optimization or use the approach that is in continuous adjoint. There's several different areas. I'm just going to highlight a few. The first one is in external aerodynamics for automotive. And most importantly, we can talk about drag reduction or lift and downforce manipulation. That would be more along the lines of changing the external, kind of the body panels of a vehicle in order to reduce drag, or maybe we're optimizing the shape of a side view mirror or one component that touches external air in order to reduce drag. Another one would be flow control. And for flow control, we might have target mass flow within a manifold, an intake manifold. We might need to have specific flow uniformity through an air box that has a filter, something like that. And we might like to increase flow uniformity to increase the lifetime of that device. Next would be swirl control. We might want to maximize the swirl that comes into a cylinder. And as I mentioned, I did a previous webinar on multi-objective optimization, and this is actually the case from that. Here we can do multi-objective optimization. Here on the y-axis we've got swirl index, and on the x-axis we've got mass flow rate. And here we wanted to maximize mass flow rate through this intake port on the top of a cylinder. And so here we see this Pareto front of these points, and we've got different designs that optimize these two different objectives. So if this is interesting, please go back and check out that previous webinar. Next would be energy use reduction, so power loss reduction or increasing volume uniformity. This is very important in subcomponent designers. So if you have something like a gear pump, or you have fluid flowing through a narrow channel in an automotive subcomponent, and you want to reduce the energy that's lost as fluid passes through those passages. Next would be material use reduction. So if you're doing things like light weighting, or you want to minimize the volume of a component, then you can also use adjoint to reduce the volume of this component. So just a little bit about the adjoint method itself. This is a very oversimplification of the entire process, but it's good. It's a good starting point. Within the adjoint process, or at least the adjoint algorithm, first we solve what's called the primal fields. Here we've got Navier-Stokes equations, we've got momentum, there's pressure gradient, we've got continuity. This is for an incompressible system. Our two variables are velocity and pressure, and we call these the primal fields. So if you've been performing CFD, you should be very familiar with these two equations. After solving the traditional CFD computation, we solve a adjoint CFD computation. So this is a set of equations that are analogous to the Navier-Stokes equations, but instead we use what are called the dual fields, or the adjoint fields. We've got adjoint velocity, here we call it U, and we've got adjoint pressure, we call it Q. So we see adjoint pressure gradient right here, we see some convection terms, and we see some diffusion terms, a diffusion term. We also see an adjoint continuity also in this equation. So there's an analog to the Navier-Stokes equation. And note that this is a transport equation. So we're using a finite volume method. We're good at solving these integral differential equations over discretized space. So we like using continuous adjoint because it uses this transport equation that we can solve with similar methods that we solve transport equations for our CFD computation. Great. So once we solve those two sets of equations, we'll compute the sensitivities. There's two different types of sensitivities. One is a surface sensitivity, and the surface sensitivity is approximately proportional or approximately equal to the normal gradient of the primal velocity dotted with the normal gradient of the adjoint velocity. Next, we have volume sensitivities. This is out in the space away from the surface, and this is related to the dot product of the adjoint and the primal velocities. Great. So what do we do with that information? Well, for surface sensitivities, we're actually given a surface map that has sign, it has magnitude, and we're given this map on the surface to tell us where to push in or pull out on a surface to, say, reduce drag or to increase mass flow. This is ideal for shape or surface optimization. I use shape and surface kind of interchangeably. For volume sensitivity, so the dot product of the adjoint velocity and the primal velocity, we're given a sensitivity that tells us where to block off or free up a cell in order to decrease pressure drop or increase flow uniformity. So we're given data out in the middle of this geometry, so not just on the surface, but out in the volume. This is ideal for what we call topology optimization. For topology optimization, it uses a blocked off, it's used to block off the region. The mesh does not change at all throughout the entire simulation, and it's ideal for what we'd call larger deformations. So remember that, larger deformations. Within HELYX, we use a level set immersed boundary to approximate this moving optimal surface. For shape optimization, it's used to actually move the boundaries. So the surface physically morphs. It requires smoothing. It may require remeshing depending on how much that surface is moved. It's ideal for small deformations. So when I talked earlier about external aero for vehicles, there's really a lot of gains that can happen by small changes in the surface of a vehicle's external geometry. Within HELYX, there's two different approaches. There's a node-based approach, and then there's this lattice-based morphing with NURBS. So overall, the workflow for continuous adjoint, and this is the same for topology versus shape optimization, there's always an initial evaluation of the current design or the packaging space. So now if you're not familiar with packaging space, this is used in topology optimization, and this represents the maximum allowable kind of space that this device can occupy. So it would be this giant box or something like that. Or if we're starting from a current design and we want to do small changes to it to improve it, we would need to do an initial evaluation. So provide baseline numbers of the objectives to determine the amount of improvement later. Next, we want to do the actual adjoint optimization and the extraction of the surface or morphed surface from the optimization steps itself. So we output this surface or we output this immersed boundary from the level set if we're doing topology. Next, we take that optimal surface, we perform an evaluation of a final design to actually confirm that that result matches what we optimized. And then finally, as engineers, we take that new information and we interpret that and we incorporate that into our next iteration of designs. Okay, so if we're given information that says, by morphing in this region, by changing the shape of the mesh or the surface or blocking off this region improves the flow rate uniformity, then we would take that into account next time we're performing a design iteration. Okay, great. Let's talk about shape optimization. So I mentioned there's two different approaches. There's a node-based and then there's a VNURBS. So let me talk about the node-based deformation. First off, it uses implicit smoothing, and it also does mesh optimization for improved deformation. So if we're moving these boundary faces into the domain or outwardly, then we want to make sure that we still maintain high quality cells. So it does mesh optimization to smooth these cells, keeps the same connectivity, but it keeps high quality cells so our simulation doesn't diverge, or it tries to do that so it doesn't diverge because of poor cells. Just an example, this approach, we're able to designate which patches are deformable, which ones are constrained. So here's an example of a drive air model. You can kind of see it. You'll need to get really close to your screen, but you can see the left-hand side right here is the baseline, and the right-hand side is the optimized shape. Now remember, we only changed this back upper panel and then the top of the trunk area right here, so you can see a little difference. Overall, there was about a 2% drop in the overall drag. So here we've got a normalized drag of 1. Now we're down to around 0.98. And so we can see improvement based on the change in shape of this vehicle. So very, very small change. So we're talking millimeters in magnitude. And so we see that over time, this does converge to a near steady state drag at the end of this optimization. Okay, great. Some important things are there's morphing and then there's smoothing. Actually, there's smoothing and then there's morphing. Just some examples of surface sensitivities right here. This was on some ductwork that was on a project with FCA. And we'll see some spikes in the sensitivities on the surface right here in this region. That's kind of the most evident. But if we use smoothing, then we can smooth out the neighbors so that we don't get these spikes. What's the potential pitfall of having these spikes? Well, maybe we'll have two regions where the mesh will be, the sensitivity will predict pulling out on one region and then pushing it on another, or maybe the two magnitudes will be not quite close to each other, so we'll see a gradient in the sensitivity. And so we'll see some discontinuities in our morphing. So here's another example of smoothing. So here you can kind of see this aliasing or ripple of the sensitivity on the surface. Here we've got that rippling that's really smoothed out. We still are able to capture the larger characteristics of the sensitivity. So here's this red region. We've got this giant blue region right here of sensitivity. We're still able to capture that by selecting the right smoothing radius. Similarly, we see, here's another one that we have some ripples in the surface sensitivities, and then we're able to still maintain that with a nice smooth transition from this region out into the bulk. And then over here, we still have a slight red region, but it's still much smoother. And this benefits us because it means that we're going to have a nice, smooth, more manufacturable transition from a going from one iteration to the next. All right, so that's node-based. The next is called a VNURBS deformation. And so the user constructs a lattice structure of points, and then this lattice structure of points is used to change and morph the surface. So that's a two-step procedure. The first one is training, in which we're mapping the mesh to the control points, and then next we're doing this deformation to displace the control points and the mesh based on the created map from the user. So here's just an animation of a simple cylinder that's being deformed. And so we see nice smooth transition throughout this whole object right here in this whole surface mesh. So in terms of input, we need to provide a number of control points in the X, Y, and Z direction and a polynomial in the degree in the X, Y, and Z direction. So you have to physically, you have to pick this control box or these box of control points on this device. So the boundary control points can stay fixed to ensure continuity between the mesh and the control points. And we're coupling the sensitivities through mapping the sensitivities to the control points, just like a mesh. And we're using that sensitivity and in order to guide us on how to morph that device on the control points. Okay, so very, very, high overview of these two different approaches. Now, let's see some success stories. I'll go over two. The first one is from Volkswagen, and this was an exhaust port modification. So we're looking at an exhaust port on the top of a combustion cylinder and an internal combustion cylinder. Yes, internal combustion engine. And we wanted to perform shape optimization to modify the geometry based on the surface sensitivities. The design objective is to maximize flow rate. So this is the current design of this exhaust port. Same picture right here. And we're given these surface sensitivities, or calculated the surface sensitivities on this device. You can see here's some examples right here. These are both published papers and presentations. There's one that's really great called The Adjoint Method Hits the Road by Karsten Othmer. You can find that presentation online. And here we have the optimized shape. So you can see right here, it pulled the surface up because we had some slow moving fluid right here. So we're going to pull this surface up into this region right here. You can also see some of it pulled over in this region. You can see some of the surface pulled together in this region right here. And we can also see that sensitivity of underneath this arm of the exhaust port. We can see that being predicted to push in or pull out on this device. So we see an increase of 5% of mass flow in the optimized design. Next, we've got a success story from Rochling, and this project was to use HELYX Adjoint to produce a duct configuration with maximum flow uniformity on the manifold lower end. So for this case, there's 3 different approaches that were employed. And so I would say that this is kind of stereotypical of how people use surface shape optimization within HELYX Adjoint. So there's 3 different approaches that were used. There was a pure surface optimization. The next one was just a pure topological optimization. And then the last one was a combination of topology and shape optimization. Just some information about the system. It was air, the density of air, we're given the viscosity of air. It's an incompressible flow. We're given a single operating point, so a volumetric flow rate at kilograms per hour. It's atmospheric pressure on the outlet. And we want to maximize the flow uniformity through these 7 different cell regions, so cell 1 through cell 7. For the first approach, we're using shape optimization. And so for shape optimization, the first step is to evaluate the adjoint surface sensitivities, as I mentioned before. Next, we want to apply a freeform lattice-based mesh deformation using the VNURBS approach that we had before, calculate the new adjoint surface sensitivities, and we repeat steps 2 and 3 until we see some convergence with an optimal shape. Next, let's talk about just the topology optimization. So if you notice, these 2 designs right here, these 2 regions, we're starting with something that's already an existing design. Okay, so we've got an inlet right here and it's flowing down this arm right here. And then we're moving to topology, so there's going to be larger deformations. So we've got this packaging space. This is the maximum possible volume that this entire device can take. So we've got the flow coming up through this region right here. And for topology optimization, we evaluate the volume sensitivities in the packaging space. We employ the level set approach to track this optimal fluid-solid interface. We apply some curvature limitation, and we do this to produce smooth ducts that are much more manufacturable than if we didn't do smoothing or curvature correction. And we do 2 and 3 repeatedly until the surface converges and we get a final smooth optimized interface. Now let's talk about the third approach. This is a combination of the 2, so it uses topology and shape optimization. First off, we run the topology optimization workflow. Then from there, we apply this free-form lattice-based mesh deformation. And so we could use the node-based approach as well. This is just using VNURBS. We could also use the node-based approach in this case. And so we take that immersed boundary, which you can see right here inside of this control point lattice right here, and we're going to perform that surface optimization on this immersed boundary. And we calculate the new adjoint surface sensitivities. We repeat 2 and 3 until there's convergence. Okay, great. So I think you have an idea over these 3 different approaches. Let's see how we can compare. So this light gray right here, this is the baseline right here. So we can see these different flow rates in kilograms per hour. And so we've got baseline, then we've got an optimized based on shape, which is this blue. Okay, great. Now remember this, or you can kind of see this hashing right here. This is actually the target that we're trying to get to with our optimization. So we can see that the current design is fairly far from the target because we want uniformity through all 7 of those cell regions. So next we've got just shape optimization, which is this dark blue. Then we have topology optimization. All right, so this is the overall morphing, large deformations. Great, so this is the maroon or red color. And then finally, for the combination of topology and shape, we've got this light green, or dark green, sorry. So within this, we see much closer, at least in cells 5, 6, and 7, we see that very close to the ideal flow rate or the target flow rate through those domains. So we can see that also with 1, 2, 3, and 4. So overall, we can see that a combined kind of a hybrid workflow of using topology and shape optimization, we're able to go even further using these 2 approaches to get a more optimized result. So just an example, here's the shape optimization optimal surface. We can see the flow rate or the normal velocity coming out of the bottom of this device. Here we've got just the purely topologically optimized surface right here. So this is the flow rate or the velocity coming out of this device. And then we see for the topology and shape optimization, we see a little bit more uniformity. So here we've gotten rid of this spike right here. It's smoothed out a little bit. So we see a little bit better uniformity within this. Okay, great. So we've got 2 success stories. One was purely shape optimization, and then we see another one, which is topology plus shape optimization. And I'd say that that second case is more along the lines of how people use this, or how customers use HELYX Adjoint. Let me do a simple setup. And so this is a U-bend pipe optimization. So it's an internal flow. There's no packaging space provided. So in the second example with Rochling, there was a packaging space that was provided. Since we're doing surface optimization, we're doing small deformations. There's no packaging space provided. We do, however, know the maximum displacement that we'd like to have in each time step. And we do know which patches can morph and which ones cannot. Here we're doing a single objective, and we just want to satisfy minimizing pressure losses in the system as this fluid takes a turn. And then we also want to be able to visualize this optimal surface. All right, so let me exit out of this and jump over here to HELYX. So let me, got this case currently loaded, but let me disconnect real quick from client server and I'll start over. So when we start HELYX, we're met with this client server connection. Here's where we can connect to different resources. This is my workstation within my office. I'm at home right now. If I want to work and perform my computation on this machine, which is a Windows machine, I can do that right here. If I wanted to, I could also connect to my cluster back in the United Kingdom or here in the US, or I can connect to a different third-party provider of HPC resources. All I need to do is set up a client-server connection, install the software at that location, and then make sure I have credentials, and then I can connect to those resources pretty easily. All right, so let me just do a local host connection. All right, so immediately we're met with this dialog that shows us recent cases that have been set up. We can start a new case. We can open up a case. Let me start a new case, and we can select how many cores we want to run on. If I'm about to submit a job to a cluster, I can submit it to hundreds or dozens of cores if I wanted to, and submit them through PBS or LSF. If I'm just solving something locally, I can choose something more realistic like 2. And I could also set up something on a lot more cores and then move the job over to a queue and submit it that way too. So here, let's just do 2 cores locally. The overall workflow is setting up a case. We're going to start in the mesh tab, start at the top of the tree and move our way down. Once we have a mesh or once we have our mesh settings, we'll go to setup, then we'll go to solver, and then we'll go to view once we have a result to look at the results. So let's start with the mesh. The meshing algorithm, I'm going to choose the default layer addition algorithm. Next, we're using a cut cell approach, so I need to create a background mesh. I'm going to select automatic, and I've done this case before, so I'm going to choose 1 millimeter as my background mesh. Next, I need to import my surfaces, and so I ran this case yesterday. So let me import all of my STLs. If I'm importing from CAD and the default units within CAD are in millimeters, then I'll need to check this box. If I forget to do that, I can always translate these. I can always transform them by right-clicking and hit transform, and then I can rescale, rotate, translate, do lots of different actions on this surface. All right, great. So we've got this group of STLs. So we've got a different STL for each surface that will become a boundary condition. I could have one single STL with several different children STLs if I wanted to. If I had one STL and I needed to split that up, it's very easy for me to just right-click and go to split, and then I'm able to select the different faces off of this device. So let's see if I can just, which one? Deformable walls. Okay. So I can select the different areas on this STL, and I could, in theory, split this off and make a new boundary condition. That's very handy, especially in this surface-based optimization, because maybe one iteration you'll notice that there's an area that you don't really want to move at all. So I can select off those patches or those faces. All right, I don't need to do anything, so let me click close. In terms of what settings I need to set on each one of these surfaces, I would like to have uniform meshing across everything, so I'm going to do a level 1. What does that mean? The base mesh is 1 millimeter, so the local cell spacing will be 1 millimeter divided by 2 raised to the first power. If I wanted to go even smaller, I could raise this. So this is 1 millimeter divided by 2 raised to the second power. All right, so let me change this back to 1. Now, I'd like to add some layers to the deformable walls and the fixed walls. If I want to, I can go to the Layers tab right here. Let me add 3 layers, just as simple as that. If I had porous media or MRF, then I could set up the zones for the porous media inside of here, and then I could set the model later inside of the Setup tab. So right now, I don't need to do anything. Next, material point. So I need to tell the mesher which side of this STL am I going to actually be performing the simulation. So if I was going to do an external arrow and looking at the fluid shedding over the outside of this tube, I'd put the point out there. But if I was doing a simulation on the inside of this tube, which is what I'm doing right now, then I would make sure that that point was inside that device or inside of those surfaces. All right, great. So at this point, it would take a minute or two on my tiny machine to generate this mesh. I could hit create mesh if I wanted to. So for now, I'm going to use virtualize mesh, which will assume that all of these patches will become, or all of these STLs will become different boundary conditions. And what will happen is it will virtualize the mesh and allow me to go on to the second step, which is the setup step. Similarly, with setup, we start at the top of the tree and work our way down. We start with solution. This is where we set the physics. So we're doing segregated, steady, incompressible. And then I have access to the adjoint toolbox. So let me select adjoint. My material is going to be air. So you'll notice immediately once I clicked adjoint and navigated to a different section, I have these 3 new tree entries that appeared. So I'll get to those here in a second. So material, I don't need to change my material, but if I wanted to, I could change that. Modeling, this is the turbulence model of the primal. So of the fluid inside of the system, we're going to use a K omega SST. Next, we've got the optimization settings. So the adjoint optimization, this is where we select if we're going to do topology, if we're going to do surface or shape optimization. So here, we're going to do node-based. And if you're curious about level set topology optimization, look back to our blog that has information about a previous webinar that I did some topology optimization. So here for this case, let's select a smoothing radius of 1 millimeter and then a maximum displacement. Let's also do 1 millimeter. Okay, these are things that as a user you'll have to experiment with in order to get the best setting for smoothing radius. So smoothing radius, if it's too large, you'll smooth out any of the sensitivities and it won't move. You may not achieve an optimal result. If it's too small, you won't smooth enough and you'll get points of, I don't want to say discontinuity, but you'll get sharp sensitivities and the cells will move in a different manner and you may get some instability. So here we can change this. So 1 millimeter was the largest cell. We're doing about 0.5 millimeter. I'd say 3 to 5 times the size of the local cell spacing. So for this case, actually, I'll just leave it as 1. Use max displacement. Next, we're going to do smoothing and deformation. If you only wanted to do smoothing and you wanted to do deformation with another software, I can choose smoothing only. Here, I would like to do deformation. I would like smooth transitions between deformable and constrained patches. I'll leave the smoothing iterations as 10. If we have a particularly unstable kind of system, I might increase the smoothing iterations. Here's where I determine or set the deformable versus constrained patches. For deformable patches, I'm going to select deformable walls, which is this region right here. For constrained patches, I'm going to select the fixed walls. All right. Next, we've got adjoint solution. Here's where we set how many initial iterations before it actually does any of the morphing of the primal and the adjoint system of equations. And then also we can control how many iterations at each optimization step. So the initial iterations are the initial convergence criteria and initial max convergence. And then while it's doing the optimization cycles, this is the number of iterations of primal and the iterations of the adjoint. For this case, I'm going to leave everything as default. We'll use 1,000. We'll use 1,000 as the initial iterations. We'll do 5. And then for normalization type, this will normalize the sensitivities based on initial sensitivity. So the first sensitivities that are calculated after initialization will be used to initialize or to normalize the sensitivities for the rest of the simulation or the rest of the optimization. The benefit of this is that the sensitivities that we use will be in a narrower range, and then also the weights, if we're doing a multi-objective, this is more important for that. Okay, and if you're curious about that, again, I did another webinar on that. Adjoint turbulence, I don't need that. Adjoint wall functions, I don't need that here. Adjoint objectives, let's go ahead and select, we're going to do pressure loss. Now we could choose from a big list of these different objectives. The user's guide will show you exactly what each one of these are. The user's guide is located up here in this top right question mark. You can go to HELYX Adjoint User's Guide and it talks about a lot of what I'm covering today. Here we want to minimize pressure loss. So I'm going to leave that as minimize. And because we're doing single objective, I'm going to leave that as a weight value of 1. If we were doing a multi-objective and I had multiple objectives, I would need to weight the importance of each one of these objectives differently. So I would say something like pressure loss was more important than swirl, or pressure loss was more important than mass fraction balance between multiple outlets. Next, I can either set the objective patches. So the objective patches in this case would be just inlet and outlet. Since there's only one inlet and one outlet, it does that automatically. I don't need to set the objective patches. All right. Next, I need to set up the primal system. So deformable walls, fixed walls, those are both walls. So let me use control, select both of those. Patch type is wall, it's stationary, there's no slip. I want to use a wall pressure boundary condition because I'm able to get slightly better results using that approach. Next, we've got an inlet. I'll set the inlet to type inlet, and I'm going to change it from velocity components to velocity normal to the patch. And this will be 0.1 meters per second. For outlet, I'm just going to set this as a simple pressure outlet, incompressible system, so it's zero pressure. Cell zones, there's no cell zones, so no porous media models, no MRF, nothing like that. Numerical schemes, I could leave everything like that if I wanted to. I can change these to first order schemes if I like to start with first order schemes, which I do. Solver settings, the residual control on the inner iterations, the relaxation factors in between iterations. I can do velocity limiters. If I notice in the very beginning there's big spikes of velocity, I can limit that velocity so that it kind of helps the convergence within the system. Runtime controls. In this case, I'll actually only need to run for about 100 iterations. And data writing, I could output every time step. If I wanted to see the surface morphing itself, I can do that. If I only care about the final result, I can just look at 100. Write format, let's use binary because we want to save some space on our hard drive. Write data, we can output ENGYS data if we're using ENGYS as a post-processor. Field manipulation if we wanted to calculate things like field averages, or if we want to do a field process, we can do a field process, and what this can do is calculate in situ data analysis or in situ derived data production. What I mean by that is I can calculate Y plus while the simulation's running. I can calculate the total pressure coefficient or the wall shear stress. Or if we're looking at noise sources, I can look at Proudman sources or vorticity. So we can do lots of different things if we know that we're going to need that for our post-processing. Let me remove that because I don't need it. Monitoring functions. We can do different reports on forces, lift, drag, noise propagations. That's Fox-William-Hawkins model right here. Pump performance, surface report, volume probes, and zone forces. Zone forces is nice because that gives us the mass flow rate and pressure drop through porous media. Volume report is my all-time favorite because this tells us the min, the max, and the mean of whatever variables I select over here and put on this list. And the reason why I like that is because it's more of a sanity check of your simulation, and it tells us great information about simulation health, saying if we see a velocity spike that's 3 times the speed of sound, but we're doing an incompressible flow, maybe there's a problem with my boundary conditions, or maybe there's a problem with a particular model that I've set or model constant. Maybe I forgot to change the units of my my geometry. All right, next we've got field initialization. Let's set up potential flow for velocity and pressure, and then for K and omega, let's do Prandtl. So at this point, if I've got a mesh, I can hit initialize. I do not have a mesh because I virtualize. So if I want to run the simulation and run the optimization, I would hit run all. This would mesh, this would initialize, and this would perform the adjoint optimization. So one important thing before I move on to the actual result is I never had to set up an adjoint boundary condition. all I had to do was set up the kind of the algorithm controls and the objective, and then how I'd like the surface to move. So we don't actually set up any boundary conditions for adjoint. All that's done behind the scenes, and it's done automatically, which makes setting up these kinds of problems much, much easier than other software. All right. So at this point, I could hit run all. We could go get a coffee and come back in about 10 minutes, and we would have a result. However, let me go ahead and load up something that has already run. Okay. So first, before we go on, let me move to the solver tab. Here, let me look at the residuals. Here we can see different plots of the primal, and then we can also see the residuals of the transport equation associated with pressure losses. All right, so we can see that going down. If we wanted to, we could also see the actual value of the objective. So we can see initially it jumped up, and then so our starting point is around 0.08 pascals. So very small pressure drop in this device. And then we see a decrease over time to around 0.066. Okay, great. So what does that surface actually look like? If we look, we've got all of our times. I wrote out every time step just because I wanted to make a nice animation. If we look at time step 1, this is after the initial iterations, the initialization step of the adjoint approach. And so here we've got pressure drop. If we wanted to, I could look at streamlines. Let's see if we can look at streamlines. And let's look at a patch source, and our patch source is going to be from the inlet. Let's let it populate all the streamlines really quickly. And then let me change the streamline radii to 0.5 millimeter, and then let's color by velocity magnitude. Let me hit update. All right, so this is just the initial condition. Great. Everything is nice and orderly going around that bend. One would think that it's hard to improve on that. So we see some twisting motion. Okay, great. So that's the first time step. Let's dive into, say, the 12th time step. All right, so we see some bulging out of this, the edges of this pipe. I made a group earlier. So this group, we can do multiple different things. So one is called groups, where we can create different things grouped together. So here we've got our different STL surfaces. I can group together the different surface meshes if I wanted to. I created a group called pipe bend. And the reason why we like that is because we're able to apply things like transparencies to help with visualization. So we'll be able to see the boundaries themselves and still see things like the streamlines. All right, great. So here we've got at about 12 iterations in. Let's go ahead and skip all the way to the very end. All right, great. Let me turn off the transparency, and then you can see the surface mesh. So we can see there's a nice transition between the fixed walls and then the actual deformable walls. So it's done a great job with maintaining a nice smooth transition between that. And we did that on both sides. And also, you know, over time, this thing has moved out, the surface has moved in, so it's done a great job with actually morphing this surface. What does that actually mean in terms of what happened with the deformation throughout this optimization cycle. I'll talk about that when I jump back to the slides. But at this point, what we could do is we could export this mesh. We could bring it back into a CAD software if it was able to convert STL, triangulated surfaces, back into CAD. You could just import the STL surface itself, and then you could manually morph your CAD with that as well. So it gives great information about where to morph the surface, where to move the surface in order to reduce the pressure drop. All right, let me jump back to my slides. And here's just a nice animation. Let me pause it just a little bit, and let me see if I can go just a little bit slower. So we see right in the very beginning, right here, right in the very beginning, we see lots of deformation. So in these higher valued numbers right here, it goes from 1 millimeter, which was our highest, down to 0. So we've got 0 millimeters down here at our fixed patches. And we see initially lots of growth. Over time, it starts to grow slower and slower. And then eventually we see less and less growth. That's good because that means that we're actually converging to a solution, meaning that the solution for minimizing this case is not an infinitely large device. All right, so it keeps getting smaller and smaller in terms of our overall step, the actual maximum displacement step. And then eventually it gets a lot smaller that it's even below the range of this legend right here, below 1/10 of a millimeter. Okay, great. Overall, we get about a 17% reduction in pressure losses. So what does that mean in terms of displacement magnitude versus the optimization cycle? Now remember, I set the maximum displacement to be 1 millimeter. So initially, at the first displacement, it was 1 millimeter. And what does that mean? It means that it takes the sensitivities over the entire domain and it normalizes the sensitivities and applies that maximum displacement. So on average, for that first step, it was about 1/2 a millimeter on average over that entire deformable surface. However, there were a few faces that were doing 1 millimeter in deformation, and then there were some that were doing 0, right near the edges of where the fixed faces were. Over time, we see the average displacement drop off, and then it gets very, very small. I mean, we're approaching machine precision. It's 5e to the -5, but if we go down much further, it's diminishing returns if we did much more than 100 time steps. But you can see that even though we chose 1 millimeter as our deformation, it dropped off tremendously by an order of magnitude within the first 30, the first 10 or 15 time steps or optimization cycles. And then after that, it dropped off almost another order of magnitude for the rest of the time. So we saw a pretty fast convergence with this case. Okay, let me leave with a few take-home messages. So I talked about the unique continuous adjoint formulation for a topology and shape optimization that we've been developing since our company started over the last 10 years. And this particular technology has been deployed in industry, and designs that have used HELYX Adjoint are actually released to market. So you can find some products that have used HELYX Adjoint to improve the design out in the wild. This has also been used on very large cases, so hundreds of millions of cells can be handled easily by HELYX Adjoint. And this is because we're using the continuous adjoint approach. If we were using discrete adjoint, it's not quite as memory efficient as continuous adjoint. So that's one of the main reasons why we use the continuous adjoint approach. And I did show that automatic surface morphing could be used for this advanced shape optimization. So this hybrid approach of using topology and then also using surface optimization to just get a little bit more out of your designs. In terms of next steps, I would say reach out to ENGYS. Let's compare results with other adjoint solvers on the market. If you have a case that maybe had a problem in another software, we're happy to look at those and talk about that. And we could also discuss how your company would like to use optimization. That's really important because, there's different ways to optimize designs. And I talked about that in a previous webinar, but, adjoint works in a particular way, and it's good to talk about what your goals are in terms of optimization, how they can be met with adjoint. And we can also talk about how you can use HELYX Adjoint within your design process. And then if we get to that point, we can talk about creating a demonstration case of HELYX and HELYX Adjoint and show you the difference that using adjoint optimization can do on your design process. And then lastly, you can follow our blog at blog.engys.com and get this recording and other webinars and other information about the work that we're doing here at ENGYS. So with that, I am finished, and I will go on and answer a few questions.